So today we're going to talk about a surprising and classic example from probability theory, sometimes called the birthday paradox or the birthday problem. And one way of formulating it is as follows. Suppose you have 23 randomly chosen people, and you want to know what's the chance that two of them, some two people in that group, have the same birthday. I think there's a feeling that the chance is pretty low, given that there are 365 possible birthdays. But we can figure it out directly. Now, if we try to approach this too directly, then we run into a problem, which is that in a group of 23 people, there are lots of combinations of two. There's lots of pairs of them, and it's unclear how to aggregate the probabilities of these different pairs having the same birthday to come up with the total probability. But we can make the question much easier without having to worry about that by reversing it. We can ask, what's the chance, given 23 randomly chosen people, that none of them have the same birthday? And that's easier because we can think of it step by step as adding one person at a time to the group and ensuring at each stage that that one person we added doesn't have the same birthday as any of the people who are there so far. So if we consider our first person, the chance that there's no pair of birthdays in common is 100% for our first person because there's only one person so far in the group. Now when we add the second person into the mix, we just need to make sure that the second person's birthday isn't the same as the first person's birthday. So there are 364 out of 365 ways that that can happen. I'm assuming here that there are 365 days in the year and that each day is equally likely to have for a person to have a birthday on that day. Neither of those are 100% true, but they're both close enough. So now we've added the second person and they've avoided the birthday of the first person. What about if we add a third person? The third person needs to have a birthday which avoids the birthday of the two previous people who are already in the group. So for that, there are 363 out of 365 ways for that to happen. And at this point in total, the chance that these three people all have three different birthdays is, well, this happened for sure. And then we needed the second person's birthday to avoid the first person's birthday. That's the chance of that. And then in addition, we needed the third person's birthday to avoid these two birthdays. So we have to multiply these. Just like when you roll two dice, the chance that you get, say, 2 6s is the chance that you get 1 6 times the chance that you get the other 6. So we're multiplying the probabilities here. Now this continues. We add the fourth person, and they have to avoid the first 3 birthdays. And we keep going until we add our 23rd person. And if you follow the way these numbers go, then that should give us 343 out of 365. So these are the chances at each stage of adding the nth person that their birthday avoids the previous birthdays that have already been represented in the group. And if you multiply all these numbers together, you can do it in Google or on a good calculator or something, then what you get is approximately 0.49. And what that means is that there's a 49% chance that when you add the 23rd person, you've got a group that have no birthdays in common. And that means that there's about a 51% chance that there's at least one birthday in common in this group of 23 people. And this is surprising. There's a more than 50% chance that in this group of 23 people randomly chosen, that 2 of them have a birthday in common.